All right, hello everyone. Welcome to the next lecture. In the past week or the past two lectures, we started with defining what the Laplace transform is. We found Laplace transform on the operators, on the step impulse functions, on other functions, for example, sine of omega t. We also did the Laplace transform on the operators, on a derivative, integral of a function, right? So today we're going to use a lot of that and apply those techniques on an electric circuit. So we're going to do one of the circuit problems as well. And again, in this part of our lecture, we're going to start looking at the applications, how those Laplace transforms can be applied on the electric circuit. So essentially, we're going to look at how this differential equations, integral differential equations, can be converted into S-domain equations, which will become algebraic equations, as we're going to realize that shortly. And then we also have to take our inverse transform back, because we're going to first convert the time domain into S domain, solve it in S domain, which is going to be much more easier. And then we're going to have to take an inverse transform back to the time domain to represent the final equation. So let's see how this entire thing will be done. So let's assume that this is your parallel RLC circuit, as you have seen the circuit before in the past chapters, where all the three elements, a resistor, inductor, and a capacitor, are connected in parallel. And if you remember, right, so this can be represented by a integral differential equation or a second order differential equation. Another important thing that is happening over here, that before the switch at t is equal to 0, the switch got opened. This means that before the switch was closed, before the switch got opened, right, so the current was just flowing in the loop at that time, and none of the current was being delivered to any of the elements. However, at time t is equal to 0, the switch got opened and the capacitor starts to get charged. Energy starts to get stored in the magnetic field of the inductor as well. Another thing, that just to keep the thing simpler a little, we're going to assume that there's no initial energy stored in the circuit as well when the switch was opened. So all the initial conditions, right, for example, the initial capacitor voltage or the initial inductor current will be 0. And what we have to do, we have to find the time domain expression, this v of t, for t is greater than 0. Okay, so let's solve the circuit, and then we will see how the Laplace transforms is going to come into play on doing this thing. Again, we are going to solve the circuit very similar to what we have done in the past. So for the next couple of minutes, derivations is going to look very similar to what we have done in the past, but I'm going to do it quickly. Again, since after the switching event, only IDC is providing the current, right? So you can practically write that all the resistor current plus the inductor current plus the capacitor current is equals to IDC. Another new thing that I'm going to introduce over here is this kind of a switching representation, you can call it that. We know that the switch got opened at t is equal to 0, which means that it was a switching event. I can practically model a switch with a step function, as I have been saying that for the past week. Now we are going to use that in kind of circuit applications. So this is switch that is being operated at t is equal to 0. Just imagine that if this switch would have been operating at t is equals to 25 milliseconds, I would have written u of t minus 25, and that 25 would be milliseconds. So again, because we also talked about how the step function can translate in time as well. All right, so here is your Kirchhoff's current law equation, where the incoming current is from IDC, and then this IDC is going is being divided and going to all the elements as well. So let's rewrite this equation. IR, I already know the IR, which should be V of t divided by R plus inductor current. Let me find inductor current, capacitor current, right? I know capacitor current of t, IC is equal to C dVc by dt. So I can just write this over here. And what is my inductor current? I need to find inductor current as well. The inductor voltage, I know that equals to VL equals to L di by dt, right? Now I can rewrite this equation as dIL by dt equals VL of t over L. Since everything is connected in parallel, so the voltage across the capacitor, across the inductor, and across the resistor is going to be V of t. So I can further replace this as V of t divided by L. I'm going to integrate both sides with respect to t and from 0 to t as well, with respect to t and from 0 to t in terms of limits of integration. So dIL of t divided by dt 0 to t equals 0 to t 1 over L V of t dt. Right? So this term is going to come out to be IL of t minus IL of 0, and I can practically do it for 0 positive. And then I'm going to get 1 over L. Again, what we usually do is over here, we change the variable of integration if the limit of integration has the same variable. So I'm going to do this thing as V of tau d tau. So the inductor current IL of t comes out to be, and I know my initial conditions, right? My initial conditions are 0 because no energy was stored in the inductor and capacitor. So L of 0 is 0. So IL of t comes out to be 1 over L 0 to t V of tau d tau. Okay, I'm going to replace this and the capacitor current from here back into the equation, into this equation. So IL is 1 over L 0 to t V of tau d tau plus capacitor current C dV by dt equals to IDC times a unit step function. So I finally got this kind of a beautiful integral differential equation, right? So this is your integral differential equation. What I'm going to do now is I'm going to take a Laplace transform of this equation, and I'm going to convert this equation into S domain, right? So let's convert this into S domain. Let me rewrite it. So it's going to become V of t divided by R plus 1 over L 0 to t V of tau. You can call it V of tau or V of x. V of tau d tau plus C dV by dt equals IDC times the unit step function. Okay, so the Laplace transform of V of t, we know that is V of s. And then we know that any constant that is multiplied in the time domain still remains that constant multiplied in the s domain as well. So the first term is going to come out to be V of s divided by R, right? So your constant just remains that constant in the time domain and the frequency domain. And we're going to realize that 1 over L is going to, since it's a constant, this is a constant, they're going to remain those constants, right? So 1 over L is also going to come out to be this. We have solved for this. In the last lecture, we solved for this integral, right? Integral as an operator. So go back and look at the operational transforms lecture, how to find operational transform, Laplace transform of the integral. And I'm just going to write it over here, the final answer. And we literally spent like 15 minutes talking about how to do it. So Laplace transform of 0 negative to t, for example, f of x dx, we did that and that came out to be f of s over s. So I am going to do this thing over here, right? Over here your function was f and over here your function is v. So I can practically write Vs over S. Now I have a constant C. In the same lecture, we also did a Laplace transform on the operator, which was the derivative, and the answer came out to be right when we did that df over dt. Go back to the past lecture, it comes out to be s of f of s minus finding the function at 0 negative. Since we know that in our case all the initial conditions are 0, we assume that, so we can potentially ignore this term. So this derivative is going to come out to be s of f of s, s of v of s, right? S of v of s. Okay, so this is good, right? And then we are left with IDC times the unit step function, and Laplace transform of a unit step function is 1 over s, which we have also computed in the first lecture, right? So it is going to come out to be 1 over s. And again, another important thing over here is remember that v of 0 negative is 0 because there is no initial energy stored. This was our assumption that we started with. Right? Otherwise, there would have been over here, there would have been another term, this one. All right, so I'm going to further. So one important thing, by the way, right? Your integral your equation, which has an integral, which has a derivative and an integral in it, is converted into S domain now, like this, which is just an algebraic equation with constants and addition and subtraction and multiplication and division. So it's a simple algebraic equation. Right, so this is nice, and now I can further simplify this equation by taking vs out. If I'm gonna common, let me take, rather than vs out, let me first take vs common on the left hand side. 1 over r plus 1 over sl plus sc idc over s. So what I want to do now is I can move this entire bracket on the other side. V of s comes out to be IDC over s times 1 over r plus 1 over sl plus sc. Another thing that you can do, if you're going to take c common and multiply s on the on both ends, on like multiply s into the bracket, you're gonna get, for example, IDC. I'm gonna take c common and move it up, IDC over c, right? And then this s will be multiplied by this to become I square plus 1 over l c, right, plus 1 over rc times s plus 1 over lc. Yes, okay. So this is S domain conversion. First, we again realize that we have this complicated integral differential equation that we term by term we took a Laplace transform and converted into an S domain equation, and from that S domain equation we ended up finding an expression for the V of S. And I know that the inverse Laplace of V of S is V of t, and I'm interested in finding V of t, right? So if I will take an inverse Laplace of this thing, inverse Laplace, I can easily find my expression V of t for t is greater or equals to 0. Why t is greater or equals to 0? Again, because of my unit step function that is only making it valid for t is greater or equal to 0. Okay, sounds good. Now let's see what to do with this thing. So this is how you can, again, convert the differential equations or integral differential equations into S domain equations and then solve for a particular unknown value or the current and the voltages. Now we're going to do an example where we're going to have some of the numbers for these elements as an examples, and then we're going to see what would the expressions comes out to be. Right? So this is the circuit that we were looking at with a resistor, inductor, and a capacitor, and this is the voltage and IDC, exactly the same thing. But now what we have is we have the value of a resistor available, we have a value of the inductor available, value of the capacitor available, and I also know what is my IDC, which is 24 milliamperes. And again, the question asks to find the Laplace transform of V of t and use it to predict the functional form of V of t. Okay, so two things. One, we have already found the Laplace transform of V of t, right? So I'm going to write this thing down. And then essentially what we are going to do now is eventually we have to find V of t, right? This V of t. So I have to take an inverse Laplace to find V of t. Okay, so I have V of s from previous slide. V of s was equals to IDC over C divided by S square plus 1 over RCS plus 1 over LC. Now essentially just put down all the values. So you get 24 milliamperes divided by the capacitor, 25 nanofarads, divided by S square plus 1 over R. R is 25 nano times, sorry, this is C, and then R is 400 plus and times S plus 1 over L. L is 25 millihenry times 25 nano. So once you're going to solve this entire thing, you are going to get V of S equals, I'm going to write the final expression, 96 times 10 to the 4 into divided by, as I can see that my denominator is going to come out to be a quadratic equation in S. S square plus 10 to the 5s plus 16 times 10 to the 8. Okay, so this is my expression for V of s with a numerator and a denominator. Great. What I need to know again, what I need to do now is I still have to find my function V of t. So this is still in the S domain, and I want to get a time domain thing. So now what we have to do is we have to do the inverse transform. Inverse transform of V of s to get V of t, right? And this is how we write Laplace inverse V of s to get V of t. Another thing that that is kind of missed in my handwriting is usually for the Laplace transformed functions, we write it with the capital letters, and the time domain signals, we write it with a smaller letter, right? So for example, this V of s is a capital Laplace transform, and let's call it like something like this. So this is the time domain, right? Which is sometimes can get mixed in my handwriting, right? But the capital V's are, or the capital letters are for the Laplace transform signals. Okay, sounds good. So I got this equation and I want to find the time domain signal. So we're going to do some more examples of how the possible expressions can come out to be in circuits, and how to find the inverse transform. Actually, this is a part of our rest of our other parts of today's lecture as well. Anyhow, let's start from here. There is something that is called as partial fractions. You may have studied in the past before, where what we do is we convert the rational fractions into partial fractions to find the solutions. What did I just said? It is going to become more clear in the next parts of this lecture, but let's just focus on this rational fraction for now. So what we have over here is 96 times 10 to the 4 is 960,000 divided by S square plus 10 to the 5 s plus 16 times 10 to the 8. What I'm going to do is, since my denominator over here, right, so denominator of s is a quadratic equation of variable s, I can easily find the roots of that quadratic equation. And the roots of the quadratic equation you can easily find, right? If you remember the formula, x equals to minus b plus minus square root of 4ab minus 2a, no, sorry. x equals to minus b plus minus square root of 4ac minus 2a. Yeah, something like that. Anyhow, find the roots of the quadratic equation. Once you're going to find the roots of this quadratic equation, you're going to get this answer. So the roots of this quadratic equation is going to come out to be, one root is going to come out to be minus s equals minus 20,000. The other one is going to come out to be s equals minus 80,000. So both of the roots would be real and distinct, right? So s plus 20,000 and s plus 80,000. So we should write it like this. Okay, so this is my v of, so I can rewrite my function v of s equals 960,000 divided by s plus 20,000 s plus 80,000. Okay, if this is your equation, I'm going to call it equation 1. If this is your equation, there is a way to solve that equation, right? And we essentially expand it or solve it by using partial fractions. So how? Look over here. I can convert this equation 960,000 s plus 20,000 s plus 80,000 equals a over s plus 20,000 plus b s plus 80,000. Right? And how to expand these equations depending on what sort of the fractions we get. I'm going to show you some different fractions and different expansion methods as well in the later part of this lecture. Yeah. Oh, okay. I also remember this thing. So x equals minus b plus minus x is equals to minus b plus minus 4ab over 2a. Yeah, I'm still confused about this. Sorry. I don't know. It's still slipping my mind. Yes, b squared minus 4ac. Minus b plus minus b squared minus 4ac over 2a. Here are the roots. Okay, anyhow. So this is your expression, right? And in order to solve this, and we're going to solve a lot of these equations. In order to solve that, essentially what you do is you do kind of two steps. The first step is I'm going to multiply this entire equation with this term, right, and see what is going to happen. And then I'm going to solve this at the first root. S is equal to minus 20,000, right? So multiply both sides by s plus 20,000 and solve at s is equals to minus 20k. So let's see what is going to happen. On the left hand side, I'm going to get 960,000 s plus 20,000 over s plus 20,000 s plus 80,000 equals a over s plus 20,000 s plus 20,000 plus b s plus 20,000 over s plus 80,000. Okay, if I'm going to solve both ends, the left hand side and the right hand side, at s is equals to minus 20,000, if I'm going to put s is equal to minus 20,000, this is going to make this entire this s plus 20,000, actually this will be cancelled over here, this will be cancelled over here. Okay, now if I'm going to put s is equal to minus 20,000, I can see that this entire term is going to become 0, right? Because s is minus 20,000 plus 20,000 is going to make the entire second b term or the entire b coefficient numerator is going to make it 0, and 0 over denominator is 0. So I'm going to get rid of the entire b part of it. So my equation will be reduced to 960,000 divided by s plus 80,000 equals a. Right, so a is going to come out to be 960,000 divided by s plus, let me go back, s plus 80,000. S plus 80,000, again we are evaluating at s is equals to minus 20,000. So 960,000 s plus 80,000 minus 60,000. You're going to get the value of the A to be 16. Okay, nice. Similarly, we can find the value of the B. In order to find the value of the B, we have to repeat the exact same thing. Now, in order to find the value of the B, what we are going to do is we're going to multiply both sides by this term, and then s plus 80,000, and then find the answer at s is equal to minus 80,000, right? So for B, multiply both sides by s plus 80,000 and solve for s is equals to minus 80,000. Okay, so that should provide you the answer. So for example, let me rewrite this thing since we are doing it for the first time. S plus 80,000, so this is the multiplication divided by s plus 20,000, s plus 80,000 equals a over, what was a? S plus 20,000. S plus 20,000, s plus 80,000 plus b s plus 80,000 and s plus 80,000. Okay, so what I did was I multiplied both sides of the equation by s plus 80,000. Once I'm going to do that, this will be cancelled out, this will be cancelled out, and I have to put s equals to minus 80,000. Once I'm going to do that, I can see that 960,000, right? S equals to minus 80,000 is going to make it minus 60,000. Equals to, I am left with, when I'm going to put s equals to 80,000 over here, this is going to make this thing 0. A times 0 plus b. So I can see that my b is going to come out to be minus 16. So a equals to 16 and b comes out to be minus 16. I can rewrite the entire thing as v of s, right? So v of s was equals to this thing. And I ended up converting it to, based on the partial fractions, converting into 16 over s plus 20,000 minus 16 over s plus 80,000. This is a much more simplified v of s, which I can easily find the Laplace transform for, right? And if you remember, we also did this thing where we take our inverse Laplace transform of 1 over s plus a, right? So this was the, if you remember, we did this thing where we did the translation in the frequency domain or translation in the s domain, right? And the translation in the s domain equals multiplication with an exponential, right? So if you're going to translate in the frequency domain 1 over s plus a, it should come out to be e raised to power minus at u of t. So u of t is actually converting it and moving it into the denominator, right? Because Laplace transform of s plus a was equals to e raised to power minus at, and the inverse Laplace of u of 1 over s is u of t. So if you're going to combine the two, you're going to get this thing. Okay, so once you have that, now let's just take an inverse Laplace of this thing. So the first term is again constant, it means constant, right? 16 1 over s plus 20,000. Let me write this thing. Minus 16 1 over s plus 80,000. So v of t is 16 e raised to power minus 20,000 t, u of t minus 16 e raised to power minus 80,000 t u of t. We can take u of t common, so n16 can be potentially taken out as well. E raised to power minus 20,000 t minus e raised to power minus 80,000 t u of t. Okay, so this is your final expression valid for t is greater or equals to 0. By the way, if you're going to just convert into t is greater or equal to 0, you can write the simplified equation without u of t as well, if you like, right? So for example, you can write v of t equals 16 e raised to power minus 20,000 t minus e raised to power minus 80,000 t for t is greater or equals to 0 without the step function, if you like, without the unit step function. But this is how practically we can solve these circuits, right? So for example, what we see in this lecture, let me summarize that in this part of a lecture, right? So we started with that we have a parallel RLC circuit and there is no initial energy stored. When we solve this circuit, and we have solved this circuit in the past many times, we realize that we are gonna get this integral differential equation. Once we get that, we took advantage of some of these Laplace transforms and converted that into this. This integral equation ends up being in the S domain. Once we find that into the S domain, we simplified it for the Vs and obtained this expression. And then we said that, okay, we got this expression for the V of S. In order to find V of t, we just need to take inverse Laplace. So we did an example problem where the values of the resistor, inductor, and capacitor are available. So we solved this V of S and found this expression, right, with some numbers rather than R and C variables. And then all we had to do was to find the inverse transform. Again, this term in the denominator, we have a quadratic equation. And then we said that the roots of the quadratic equation are going to be S equals minus 20,000 and S equals minus 80,000. So we can kind of expand the quadratic equation like this, S plus 20,000 and S plus 80,000. And then we can use the partial fractions to convert this thing into this thing. And then I'm going to show you some more expansions in the next part of this lecture. And then there's a way to solve the partial fractions, which essentially is that you multiply it with one of the roots on both sides and then also solve the both sides at that root. So once we did that, we find the value of the A, right over here, 16. And when we multiplied it with the other root and find the value, we found the other value as well, B. We ended up putting both of these values to further simplify V of S. And then we said that, okay, this looks pretty similar to this inverse Laplace transform that we know. So we ended up just using this Laplace transform and ended up finding that time domain signal. So this is how you can very easily convert the circuit's integral differential equations into Laplace transforms, and then also can do inverse Laplace transform as well. Alright, so with that, thank you so much. I'm going to talk to you in the next lecture where we're going to get two more transforms.